It's time for Angelo Rendina to talk us about Dockerizing and deploying a full stack Rust plus WASM web application. Thank you very much.
Right. Thank you. All right. Welcome and thanks for coming to this very late talk. I'm Angelo Rendina. I'm a software engineer at Prima Assicurazioni. And as mentioned, I'll be talking about Dockerizing and deploying a full stack Rust and WASM web app. So the talk will be divided into 3 sections. One where I introduce the tool set that I've used and the main technologies. Then another one for the actual development in Rust. And then a final section where I'll talk about how to build the images for release and how to deploy those. So for the main technologies, first, just what the app is. Obviously, I went for the smallest, non-trivial toy example that I could think of, which was a simple to-do app. So there will be a backend, which is responsible for creating and updating and deleting memos. There's going to be a persistence layer hidden behind it, and then a beautiful front end to interact with this backend, as you see here. So this is what I'll create. The architecture of this app is, as you see here, as mentioned, a database which is hidden behind the backend, and the backend exposes a CRUD REST set of endpoints. And then there's going to be a content distributor where we serve the static files for the front end, which is actually going to be a single page application rendered on the client side. For the development, the main tools that I've used are, well, a number of them, but the most important ones are Cargo Make, which is a task runner. And it's useful because you can define all the flows that you need in just one place. Then there's SQLX, which is both Rust Crate, which is used to interface the backend with the database, and also a CLI application, which is used to set up the database and in general interact with it from your local machine. Then I used Actix, which is a Rust web framework, and that's going to be used to spin up the HTTP server and to build it into a native executable. And finally, for the front end, I used U, which is a Rust WebAssembly front-end framework that is used to create single-page applications. On the infrastructural side, everything is containerized using Docker, and that allows me to run the dev stack locally using Docker Compose, and then also to build the release images that are going to be deployed through Kubernetes. And in particular, to test the production environment locally, we can use Minikube. So we can check if the Kubernetes setup is correct. So about the local development, first of all, a few words about the database. So yeah, we first of all need to define a schema so that the Postgres database is set up correctly. And here, instead of running the command manually, so you see there in the bottom right, I would have to run cargo SQL migrate and create a new migration. I just wrapped it up in a cargo make flow, which is called DB migration. And the utility of this is that I can define it in just one place, which is the makefile toml file. And I can also apply some changes and modify and enhance these tasks using profiles. So in this case here, you see that under the profile called local, I set up an environment variable called database URL, and you see it just connects to the database on localhost. And there on the left, you see that when I run cargo make DB migration, I can pass a profile so that I can apply some changes on the fly. And then that memo in the end is just used to generate the migration file. So this migration file, which is generated, is going to be called, some timestamp memo SQL. And in there, we can define the table. So this is just a basic SQL. And once I have that, I can run the migrations against my database. So again, here I've defined a new cargo make flow. You see, it's called database setup. And again, it would run CQLX database setup using those source, but I've just put it in a flow. And again, I can reuse the profile that I made earlier called local, so that the tool, this CLI application knows where the database is located. And the utility of this is that I can reuse this exact same flow later on, for instance, to set up the production database, because all I need to do is just create a new profile which contains the actual database URL for the live production database. But the task is going to be exactly the same. So for the Rust code, I ended up using a monorepo approach in just one workspace. So in this cargo workspace, I've created two binary crates, one for the backend and one for the frontend, and then a library called common. And in common, obviously, I will put all the shared types and functionality that is used both in the backend and in the frontend. And the advantage of using cargo workspace is that I have everything in one place. I have tools like Rust Analyzer that allow me to quickly develop on all fronts. And nonetheless, I can compile and build each individual package separately. So as I mentioned, I'm going to put all the shared types and functionality in the common crate. So here, just some examples. I have a data transfer object called memo, which obviously contains the information that are needed, both in the backend and in the front end. And then down there, you also see an update memo data transfer object. And obviously, this is going to be sent from the front end to the backend to inform what memo to delete. And again, the magic happens through serialize and deserialize, because these Rust types are used in both crates, but then in the actual use case are going to pass through the network, probably serialized into JSON. But nonetheless, I can use this one type defined here and use it everywhere. So for the actual backend, first of all, we have set up the database. We have some types. So the first thing to do is actually know how to make the database interact with the data with the backend. So here there's this index function, which, as you see, returns a vector of memos, and you see that that's a common memo, so it's taken from that shared library. And all this function does is just run a SQL query through the SQLX query as macro. But the important bit here is that you see the first argument of this macro is actually a type, and this allows us to check at compile time if the query will actually instantiate the right type. So to do this, SQLX actually needs a live connection to the database to actually poll the database to check if the type is compatible. Later on, I'll show how to disable, well, not really disable, but override this check using the offline mode. But anyway, the advantage is that we know at compile time if the query produces the right type. So once we have that index function, we can use it in an endpoint. Obviously here, this is just a get memos, so nothing fancier. This is just going to fetch the list of all memos that are available. And in this case, the code is pretty easy. It just calls that index function, it awaits it, and then if it's an OK, it returns a OK response with the list as a JSON, or it returns here just a internal server error. And you see that here, the getMemos function takes an upstate parameter, and when we call index, we actually pass upstate.pull. So this upstate is just a container for the state of the application. In particular here, within this state of application, we maintain a Postgres connection pool that we use to make the call to the database. And finally, in the main function, we instantiate the HTTP server, which is going to listen on port 3000. And the constructor of this HTTP server is actually a factory. And this factory will spawn a new Actix app, which will take a reference to some upstate Here you see that it's upstate.clone because really is an arc. So what happens is that somewhere in the main, we create the upstate, and then we pass references to it through to all the other apps. And then this app will serve the endpoints and handle those using the callbacks. For instance, here you see that a get to the root will be handled by the getMemos function that was in the previous slide. So the way the Actix HTTP server works is that it runs on the main thread, and for every incoming connection and request, it will spawn a new thread and run this, instantiate a new Actix app that will serve that request. And in this way, we can serve multiple requests at once. So how do we run this backend locally? So here you see that I've defined a new profile called Docker. And here, again, we have a database URL, but you see that here the difference is that the location of this is not localhost anymore, but it's Postgres, because when we run the backend locally, it's going to be inside the Docker network, where also the database is located. And so within the network, the backend is going to find the database at the name of the service. And then we define also a task called backend run. And obviously this is just going to be cargo run the backend. And then for the actual service, we start with the Rust image. We sync the code. So you see the first volume is syncing the local to the folder up, but also we cache the artifacts. So we actually put the .cargo and target folders into separate volumes. And obviously this is going to be useful if you compile inside of Docker, inside of the container, so that you cache the artifacts, you cache the dependency that you downloaded, and you don't need to rebuild everything every time. And finally, the command is just going to run the backend run command, which was defined in the previous slide, using the profile Docker. Again, profile Docker, because when the backend starts, it needs to establish a connection to the database, and we use this database URL environment variable to actually know where the database is located. So for the front end, I used U. So I'll say a few words about U, which is a Rust WebAssembly framework to build single-page applications. So the core of U from the developer perspective is composed of component, which is a trait that U provides. And this trait has a basic interface made of a view and an update function. So the view function is responsible for describing how to convert the state of the component into actual HTML. So what to see, what to view of that state. And update is a callback that gets called by the U runtime and is used to update the model based on what events happened. So on the right-hand side is what we actually write. So on the right-hand side, we implement components. And on the left-hand side, instead, is what the U runtime provides, which is it first is responsible for automatically creating the HTML based off the code we write, and also hook the HTML events into the runtime. And the runtime is the one that actually dispatches messages to our components. And also messages are the way different components interact with each other. So the root component is essentially where the front end starts. And you see that here in the first line, I define a struct, which is called up. And the state of this up is just a vector of memos. And again, notice here that I'm reusing the same type, the same common memo type. And then I implement this component trait for up. And so the first function we need to implement is view. You see that it takes self and context. Context is basically just a reference to the runtime, essentially. And what the view does is take the state and generate some HTML that's going to be displayed. In this case here, you see that the root component essentially is going to have, well, a box where we can input the new memo, which is not displayed here in the bubble, but also it displays all the memos that are actually there. And you see that what we do here in the code is we take the list of memos that we have, we map each of those into HTML using the HTML macro from U. And the HTML that we generate is, for each line, essentially, we generate a new viewer component. Viewer is just another component that is defined in the code base. It's just not displayed here. But viewer, again, is going to be exactly like this app. It's just going to be another struct that implements component. And when we generate this view, we also pass by reference the value, which is just going to be the text of the memo to show, and a callback called onDelete. And that callback is going to be called by the child component, in this case viewer, when it wants to signal to the parent, in this case the root component, that we wish to delete a memo. So in particular, in this case, you see that when that onDelete callback is called, we just issue a message of type delete memo to this component. And down here, instead, you see that the other function we need to implement for app is update, which is going to take, again, self, the context, by reference to the runtime, and the message that it receives. So in particular, in this case, we see that in the match of the message, we listen for the delete memo type. And when that event, when we receive that message, we invoke the function delete memo, using the common delete memo payload. And this function, this delete memo payload, is defined here, and it's just going to make a HTTP call to the backend. So you see that all it does is just spawn WASM future to run code asynchronously. And all we do is we just make a delete call to the backend, using the payload as body. We send it, and then if everything is fine, we send again a message to the runtime, to the component itself, saying, okay, the memo was deleted, and obviously this message needs to be listened to by the component to actually react to it. In this case, probably when this event is listened to, what we want to do is delete that particular payload from the list that is that is stored in the app component. So just a word here at the top, you see that I'm actually getting the backend URL at compile time using the env macro. The reason for this is that the code that you see here at runtime will actually be executed on the client machine, because when we build the front end, we just package the WASM and JavaScript and HTML into static files that the front end just serves, and so the client will fetch these files and execute on their machine. So obviously they won't have a backend URL environment variable. So one of the possible solutions to this is just read the value of the backend URL at compile time and are coded into the compiled files, so it's there. So once we have the code, again, we can define a task called frontend run to actually serve the frontend. In this case, we use trunk, which is a tool to both build the JavaScript and WASM and HTML bundle, but also to serve it in development mode so that we can actually access the frontend. And then again, we just create a simple service in Docker Compose, starting from Rust. Again, we sync the code, but we cache all the artifacts. In this case, it's .cargo target and also .rustup. And in this case, .rustup is because to compile you actually need to have the WASM32 target. So I'll say a bit more about later. But then again, the command is just going to run this front-end run task that I've defined in the previous slide. So nothing fancy here. All right, now we can go to the deployment. So first of all, we need to build the release images, because so far we just had a local stack for development purposes. So to build the backend, remember that I mentioned that CQLX uses compile time checks. So when we build for release, we probably don't want to have access to a live database just for the compilation. So the solution to that is using SQLX offline mode. And basically, instead of requiring a live database every time we compile, we generate beforehand a schema JSON file, which contains all the needed metadata. So SQLX can generate that for us. And to do that, we need to run cargo SQLX prepare. And so when we run that against any database, in this case, we probably need, well, we need to generate this file just once. So we run the database locally, we prepare the file, we're using SQLX prepare, and then once we have that file, that is cached there and is good to go. So once we have that SQLX schema JSON file, we can define a profile called release. And here you see that I actually enabled the SQLX offline mode. I'm passing the database URL environment variable from outside, and this is going to be clear in a second why. And we define backend build task, which obviously just going to run cargo build for the backend in release mode. And now we get to actually building the release image. So here I decided to use a multi-stage approach because one, it allows to parallelize some of these steps, and two, probably most importantly, Docker automatically caches all of the steps that have not changed since last build. So in this case, for instance, the very first step is to take Rust and install the cargo make command. So once we run this once, this step will not be executed again next time. So we actually cache this base step at the top. Now, the second step is called builder, and it resumes from base. And what we do here is we just take the source code, we copy inside the image, and we run the backend build command that will actually generate the binary. So here you see that I'm actually accepting an argument during build, which is called database URL, and this is so that you see there at the top, when we run the build step, we can actually pass the database URL as parameter. And this obviously is useful because, for instance, during CI, you want to generate the image so that it points to the right location related to where the deployment actually happens. So the third step, which actually happens simultaneously, is runner. And here instead, we start from Debian Buster Slim, which is one of the smaller images that can actually run the binary that we generate. And actually is not sufficient, so we also need to install some dependencies. And you see here that I need to install the libssl1 dependency. But then again, this step is going to be cached, so we do it just once and then it's good to go. And then finally, which is actually the step that generates the final image, we start from runner, which again is probably going to be 50 megabytes, so it's quite small. And in there, all we need to do is just take the compiled binary that lives in the builder stage. We just take the executable, we put it inside the image, and then we can just set the default command to be memo backend, which is actually just going to run the binary. So this way we generate a small image that is able to run the backend. So for the frontend, very similar story. We define a frontend build task, which just runs trunk build in release mode. And this will just generate the final bundle and will not serve anything. Again, we use a multi-stage approach. So we have the first step, again, which is base, which starts from Rust and installs all the needed dependencies. And you see here that we actually need to install a bunch of stuff. So we need to install the tool chain for RustUp. We need to add the target WASM 32 so that the compilation can take place. We also need to install trunk, which is used to build the static package, and also WASM badge and CLI. So once we have that, which is again cached and is only going to happen once, we have the builder step, which resumes from base. And again, here we just take the source code and we compile it. And then finally, we are going to take just the bundle from the builder stage and put it in this HTTPD Alpine image, which is a small Apache image, which is just going to serve the bundle that we generated. And again, here the goal is to have a small image that we can deploy. So finally, a few words about how to deploy this through Kubernetes. So the architecture that went for is as displayed here. So we have an ingress, which will accept connection from the external of the cluster, and will route the traffic to either the backend or the frontend, depending on what the host of the request is. The traffic will go through a cluster IP, which is either a backend or the frontend, and the cluster IP is the one that is responsible to actually dispatch the call to a running pod. And we're gonna have a number of pods for the frontend. There you go. Number of pods for the front end and for the back end. And also you see that, as I mentioned earlier, the database is actually hidden, is not exposed externally to the cluster, and the database is only visible internally under the Postgres cluster IP, and only the backend can access it. So just a few words about the various terms that I've used. So we have a deployment, which is used to manage pods, essentially to spin up containers from certain images. In this case, this deployment is going to take, you see there at the bottom, the memo backend image that we generated earlier, and is going to create pods based off that image, and each pod is going to be tagged with the label app backend. And then we also have a service, which by default is a cluster IP, so it's only visible inside of the cluster. And what this service does is dispatch calls to the backend service to any pod which is marked with the right label. In this case, any pod which has the app backend label. And finally, we have the ingress, which is another kind of service, but this one instead is used to route traffic from the external of the cluster. And in this case, what we want to do is fork depending on what the host of the call is. So if it was a call to backend.mimo, we want the traffic to go through the backend service. And instead, if it was for frontend.mimo, we want to route the traffic through the frontend. Finally, to run the deployment locally, I used Minikube. So to use Minikube, I need to first build release images. So again, I've used the two commands that I've shown earlier. The one thing to notice here is that for the backend, I actually need to provide the database URL, which is add location Postgres service. Again, because the backend and the database are inside of the cluster, so we need to refer it through the service name. And instead, for the front end, I need to pass the backend URL. And instead, here the backend URL is going to be relative to the client that actually execute the code. So it's going to be in HTTP backend memo. So once I've generated the images, I need to load them into Minikube. I need to apply all the configuration using kube control apply and all the files. And then finally, once I have everything running inside the local cluster with Minikube, I need to tunnel so that the local cluster is visible under localhost. And once I've done that, I just need to define new hosts in etc hosts, where obviously I just want to map backend.mimo and frontend.mimo to localhost, so that essentially when I go to the browser and type in frontend.mimo, the traffic goes to localhost inside Minikube, inside the cluster, and then from the ingress to the actual frontend pod. And that's it. So thank you for your attention.
Okay, it's quite early, so do you think you can have some demo of what you have done, or it's too hard to ask?
I can probably try to make it run, but I don't know if it's going to be fast enough. So okay. I could give it a go while. Okay, I guess. Was it too fast? Oh, half an hour. All right.
In the meantime, if you have some question, you can think about it.
It's going to take a while to run Minikube because it's not running at the moment.
Okay, so let's go for the questions.
Hi, that's some awesome Docker file stuff you've done. And I love Docker files, though I'm not a fan of Docker itself. But one of the problems I get into, particularly with junior people, is I say, okay, you've got this lovely Docker image, so how do we run the debugger on that? And then there's confusion and loss, and of course, nobody knows how to bring the application up on their desktop because it's all Dockerized and micro-Kubernetized. And so actually we never get to debug. So I'm wondering what your approach is in this environment to be able to debug what you produced. And that might involve, needing new crates or something to do the debugging or whatever. Right,
yeah. I'm not particularly proficient with actually debugging Rust code, as was already mentioned a few times this afternoon. I've done it, as you mentioned, when you run the code locally, you can debug, but I'm not really used to do that. Especially, I mean, if you run the development stack, you have a bit more access. And what I usually do again is just print stuff where I need to check what's happening. So again, not very smart solution there. And instead, probably for the release images, I guess you would probably need to put a lot of tracing and a lot of observability. But yeah, debugging is a bit tricky. So I'm not entirely sure how to do that through Docker. That's a downside indeed. Yeah.
Any other question? Yeah.
Hi there.
Hello.
Thank you for the very detailed example. I was wondering, why did you choose to put the n variables at build time instead of passing them at runtime? Since you chose, of course, cleverly to not to use the offline mode of SQLX, so you don't actually need the database URL to build your image, and even the front end endpoint, I guess you could have chosen to pass it at runtime, right?
Yeah. So for the front end, as I mentioned, the issue is that where is it? This is also mentioned in documentation of trunk, is that it's really tricky because, again, this code is going to be executed on the client machine. So, and obviously you don't have the environment variable there. So what you can do is either do this, as I've done, so do it at compile time, or you need to basically do server-side rendering. So when you serve the bundle, the WASM bundle, instead of passing this hard-coded value, you need to interpolate it when you serve it, and then obviously you can do it on you can do that at runtime. The downside with that is that I couldn't use just the basic Alpine image. I would have had to to create a HTTP server just to do this, and so I went for the simple solution of just hard-coding it. So for the front end, you can do it at runtime, but it requires server-side rendering, at least for this bit. And for the backend, there's really no reason why. It's just that I started doing it at runtime, then I had this issue with the front end, and so I said, all right, well, I'll just do a uniform approach, and I'll also have the configuration at compile time for the backend and call it a day. Yeah, for the query as macro, which again requires the offline mode. I think here, the rationale is offset because SQLX provides this awesome compile time check, so that you know while you're developing if you're breaking stuff, right? Because you have a running database, you try to execute stuff, and you will have a failure at compile time rather than at runtime. So this is definitely needed. And but to use these, you need either the running database or offline mode. The location of the database could have been done at runtime. That would not have been a problem, but it was just simpler to do it like that.
Thank you. Any other question? Yeah.
Per front end, do you have like a issue for size of the artifacts? I know that Rust built something big. Do you have any suggestions to reduce the size or like stripping the bugs? Do you have anything?
Yeah, I haven't looked at the size of the front-end bundle. I know for sure, as you mentioned, that when you compile binaries, you can, after compiling in release, you can compile for size, and you can also strip the bug symbols. That's definitely something you can do. I honestly have no idea how it works for the front-end. I haven't checked. I don't know what the size of the front-end bundle is. So I wouldn't know exactly how big, like, for instance, the WASM file is. Probably, I don't know. Looking at the trunk documentation, I didn't find any warning about that. So I'm not even entirely sure that trunk, for instance, supports stripping anything. I don't know if it already compiles for size. But yeah, that's definitely a good point, especially when you're talking about front end, obviously, yeah.
Thank you. Any other question? I think no. So thank you very much, Angelo, for your talk.